Welcome to lecture number 13 of the course Nonlinear Structural Analysis, Theory and Applications. So, let us recall what we have done so far in the course. In the last few lectures, what we have done, we have looked at three different sources of nonlinearities, right. And depending on how we want to capture them, we can perform different levels of structural analysis, right, that we have discussed in the last few lectures. Okay. So, today what we want to do, we want to look at some solution strategies for nonlinear problems. This is still in the introduction stage. Okay. Later on, there will be a topic completely on the nonlinear static analysis of structural systems and components. Okay. So, this is just to give you an introduction to some solution strategies. Okay. So, let us get started. So, in this topic what we will cover, or in this lecture we will cover the equilibrium equation, incremental solution method, incremental iterative solution methods. Okay. So, let us recall for a linear problem, if you look at lecture number 3 or lecture number 5. So, what we have written or what we have derived, R is equal to KR plus R0. What is capital R, or the uppercase R is a vector of externally applied loads, right, and K is the structure level stiffness matrix, little r is the vector of displacement at the structure level, and R0 is the vector of fixed end forces, right. So, this is fine for linear problems. Now, for nonlinear problems, what we will do, we will call this R superscript E, that means external load vector, and this is basically the vector of internal forces all along the same degrees of freedom that are defined at the structure level. So, we will call this Ri, and these is basically, if you recall, these are fixed end forces, right. So, for a nonlinear problem, if you recall, in one of the lecture we did a simple nonlinear problem. Okay. So, we can write down the external force vector minus the internal resisting force vector minus R0 is my unbalanced force vector. Okay. Why it is unbalanced, you will see. So, what we have done, I have rewritten the same equation where I am using Re, Ri and then R0. Okay. So, this is called the unbalanced force vector, which is a function of the displacement vector R. Why? Because if you recall, this is a complex nonlinear function of the displacements, right, which I have demonstrated earlier, right. So, how do you construct this? Well, to construct this, if you remember, we determine S. What is S? The forces at the element level in the basic or deformation coordinate system. Then from S we go to P, then from P we go to Q. P is the force vector in the local coordinate, Q is the force vector in the global coordinate, and then we assemble them to get the Ri, the internal resisting force vector. Okay. So, note that often this unbalanced force vector is also called the residual force vector or out of balance force vector. This means the same thing. Okay. So, what I said earlier, Ri is a complex nonlinear function of R. So, if you look at lecture number 9, you will see that example. So, equation 1 cannot be formed and solved for realistic problem. So, this equation we cannot actually form and solve for realistic problem. Solve means determine R directly by solving this set of nonlinear equations. So, here if you have n degrees of freedom, meaning that the kinematic indeterminacy of the problem is n, then you have got n such equations. So, it is not possible to solve this nonlinear simultaneous equation and determine R, which I have demonstrated in lecture 9 with just 1 degree of freedom system. Okay. So, what we need to do? We need to incrementally apply the external load and solve a linearized problem for each load step. So, let us say you have a structure, we want to apply 100 kilonewton load on the structure, right. So, what we will do? Okay, at every step I can say I will apply 5 kilonewton. So, there will be 20 such steps. Okay. So, for each load step we will solve a linearized problem, and how we solve that, that is the topic for discussion today. So, what is the problem statement then? Given that a structure is in equilibrium at the nth load step. So, let us say you have applied 10 kilonewton and the structure is in equilibrium, okay, with displacement vector R sub n, that is at the nth load step. That means, my external force vector is in equilibrium with the internal resisting force vector and it is equal to 0, but I am calling that RUN, the unbalanced force vector, because you will see in a minute that this may not be exactly 0. Okay. So, let us say this is 0, then the objective is to determine the displacement vector at load step n plus 1, where R n plus 1 is R n plus the incremental displacement vector delta R n that satisfy the equilibrium equations at load step n plus 1, that is the external force vector at n plus 1 minus internal resisting force vector at n plus 1 is equal to 0, and I am calling this the unbalanced force vector R u n plus 1. Recall that R u is a function of the displacement vector, because the R I is a function of the displacement vector, and for this course we are assuming that R e is independent of the displacement vector R. There are examples where the external force vector can change direction depending on the displacement of the structure. We are not discussing those things here. Okay. So, let us first develop an incremental solution technique. Okay. So, the internal resisting force vector at n plus 1 is a function of R n plus 1, which I have written as R n plus delta R n, right. So, this is a nonlinear function. What we can do? We can do a Taylor series expansion of this about R n, which will give me, if I go back to the previous equation, which is this equation. So, I am rewriting this equation, okay, where I am doing a Taylor series expansion of R I n plus 1. So, if I do that, then R u n plus 1 is the external force at n plus 1 minus this is the Taylor series expansion of this R I n plus 1. Okay. So, there are higher order terms, and this we want this to be equal to 0. Okay. What is this called? This is the partial derivative of the internal resisting force vector with respect to the displacement vector, right, del R I, del R evaluated at R is equal to R n. So, this is called the Jacobian or the tangent stiffness matrix of the system. So, we denote the tangent stiffness matrix using K sub t. Now, if I neglect the higher order terms, right. So, what I can do? I can say that this quantity is equal to my K t. So, K t into delta R n, okay. So, K t into delta R n is equal to the external force vector minus this internal resisting force vector, because the right hand side is 0. This is what we want. Okay. So, K t into delta R n is this. Now, I can rewrite this quantity as external force at load step n plus the incremental external force, right, minus this. So, now what is this quantity? So, this delta R E n I am keeping. Now, what is the difference between the two? Well, the difference between the two is the unbalanced force at the nth load step. If at the nth load step the structure is exactly in equilibrium, meaning that the unbalance is exactly 0, it will not happen, as you will see soon. So, if it is exactly in equilibrium, then this will be 0, otherwise it is non-zero. Okay. So, this is basically the derivation of the equation that we will be solving. What kind of problem is this? This is basically we are solving simultaneous equation. Here I have the tangent stiffness matrix, and delta R n is equal to the incremental external load plus the unbalanced force vector from the previous load step. So, we can determine this delta R n, the incremental displacement. Once I know this, I can determine R n plus 1, which is R n plus delta R n. Okay. Now, let us do a physically meaningful derivation of this instead of starting with the Taylor series. Okay. So, what if I subtract equation 2 from equation 3? Now, what are these two equations? Let me show you. So, equation 2 is the equilibrium equation at load step n, and equation 3 is the equilibrium equation at load step n plus 1. So, if I subtract 2 from 3, then what do I get? I get this external load minus this external load, so which is the incremental external load, and this minus that, which is the incremental internal resisting force vector, and that is exactly what I have written. So, this minus that, and this is R u n plus 1, and this is R u n. Okay. So, now what I am writing, this minus that is the incremental external force vector, and this minus this is the incremental resisting force vector. Okay. Now, what we want? We want this to be 0. Okay. The structure is in equilibrium at the nth load step. we want the structure to be in equilibrium at the n plus 1th load step. So, that means we want this quantity to be 0. Okay. So, what I am doing? If this is 0, then I am rewriting delta R E n minus delta R I n, and this I have taken to the right hand side, R U n is equal to 0. Okay. Now, so this I have repeated from the previous slide where we stopped. So, what we can do, let us consider that this is my internal resisting force vector and this is my displacement vector. Now, I am showing a 1D plot, right, where this is just a scalar and this is scalar, and I am using boldface to remind us that these can be vectors. So, it is easy to demonstrate for a 1 degree of freedom problem. So, let us say this is internal force and this is the displacement, and this is the actual or exact behavior of the system or exact internal force path. If you apply displacement, this is how the structure is going to respond. It is nonlinear. Okay. Now, at nth load step, my displacement is R n, my internal resisting force vector is R I n, and we are at equilibrium here. Okay. What we are looking for is the displacement here, right. So, what is the resisting force here? R I n plus 1. What is the displacement here? R n plus 1. If I join the 2 points here, then the slope is called the secant stiffness, right. So, as you can see, the difference here, this difference here is the incremental internal resisting force vector. So, which I can write the incremental internal resisting force vector is equal to the secant stiffness multiplied by the incremental displacement vector. But unfortunately, we do not know this. To form Ks, I need to know this. If I know this Ks, then I can easily determine what is delta R n, but I do not know because Ks depends on R n plus 1. But what if I reduce this delta R n, the size of the displacement increment reduces, okay. As it reduces, can I say that Ks basically tends to Kt, the tangent stiffness. Imagine this is reducing. So, if this keeps reducing, then Ks can be approximated using the tangent stiffness. So, that means here instead of Ks, I can write Kt. So, if I write Kt here and go back to this equation, okay, then what happens? Then this becomes Kt into delta R n. Okay. So, I will take that to the right hand side, then what I get is the same equation Kt into delta R n is equal to delta R E n plus R U n. That means, the tangent stiffness times the displacement increment is equal to the external force increment plus whatever unbalanced force vector I had from the previous load step. So, I derive the same equation from a more physically meaningful approach. Okay. Now, this equation is actually called the Euler's method. So, let us look at it. So, let us say I am plotting R. The reason I am using R not Ri or Re, because I can show on the same vertical axis both internal as well as external forces. So, I am using R, and this is little r, which is my displacement vector, and this is the exact equilibrium path, right. Okay. So, if I apply some external load, what is the solution that I am calculating? First, imagine that this is, I am ignoring this, okay. So, I am just solving this equation. So, my incremental external load is equal to tangent stiffness times incremental displacement. If I solve that, what I am doing? So, this is the incremental load divided by the tangent stiffness. So, that brings me to this point. Okay. Now, at this point, so I am here, at this point I apply further incremental load. Okay. So, here I draw a new tangent. Now, what is the tangent here? The actual curve is here. So, this line is parallel to this. Okay. So, I come to this point and get the delta R1. I apply the next increment, okay, and use the tangent stiffness. So, this line is parallel to this, which is the tangent drawn at that point. Okay. So, this way, as you can see, I get the solution. Okay. For incrementally applied load, I am solving a linear problem in each load step. The force displacement relationship within a step is linear. I am solving a linearized problem for each load step. What do you see? You see that this is my exact force displacement equilibrium path, and this numerical solution is actually drifting away from the exact solution, okay? Because the RU, the unbalanced force, keeps increasing, right? Now, there is a way we can reduce this unbalanced force from growing so rapidly. If we consider this RU, which I said 0, let us say if we consider it, if we do not ignore it, it is non-zero. We know it is non-zero. For example, when you have determined this displacement here, so this is the applied load, but actually you are at that point. So, let me show you somewhere here where let us say this is, or let me go back to the previous figure. So, we are let us say here, but the actual resisting force is this much. So, this is the unbalance, right? We cannot ignore it. So, if we do not ignore this, that means if we do not ignore this, then we can get a slightly improved solution. What is that improved solution? That improved solution is given by this green, okay? So, what happens I will explain. Let us say we are at this point, okay? So, what is the unbalance? This is my unbalance, right? When I am calculating or applying the next increment, so this unbalanced plus this additional load, now I am drawing a tangent here. So, it takes me to that point, okay, which if you start from the beginning, you basically get a better solution than the red, and this is the exact solution. You see, at this level of force, this is my displacement, whereas this numerical solution using the Euler method is giving me this solution. So, they are far off. How can you improve it? Well, you can reduce the step size, okay. But the problem with this is that at every load step, you have to form the tangent stiffness matrix. For a large structural system, forming the tangent stiffness matrix is not so easy. Easy in the sense it is computationally, not so easy in the sense it is computationally expensive, okay. So, therefore, you have to use many steps and form the tangent stiffness matrix every time. So, which makes it computationally expensive. So, therefore, avoid using Euler's method for nonlinear problems. So, we have better methods that we will discuss, but before we get into that, let me show you a very simple problem, okay, where a nonlinear, we have a nonlinear spring. So, this is a nonlinear spring, okay, and I am modeling that, showing that using a truss element. So, this is my displacement and this is my external force, okay. The tangent stiffness of the spring is given by this equation. So, Kt is equal to K0 into 1 minus 2r by L, okay. L is the length of the member and r is the displacement. So, as you can see, the tangent stiffness depends on the r, okay, and given that L is equal to 2 unit, K0 is equal to 20 unit, and then I want to determine using 5 increments the displacement for RE, the external load is equal to 10 units. So, I want to apply 10 unit of loads in 5 increments. So, that means in each increment I will be applying 2 units of load, okay. So, let me see the solution. If I ignore that unbalanced force from the previous load step, then this is the solution, this red, this is the solution that I get, and this is my exact solution. Can you tell how did I determine the exact solution? Well, that comes from the definition of this tangent stiffness. So, this tangent stiffness defines the force deformation behavior of this. How do I do that? What is the definition of tangent stiffness? This is 1 degree of freedom problem. So, we can write the derivative of the internal resisting force vector with respect to the displacement is my tangent stiffness, which is equal to K0 into 1 minus 2r by L, okay. So, now if I integrate this, dRi, okay, is equal to K0 into 1 minus 2r by L dr. If I integrate this between 0 to Ri, okay, and this is 0 to r, then I will be getting an expression for Ri, which is what I have plotted here, okay. So, again observe that the numerical solution is drifting away. If we do not ignore the Ru from the previous step, well, the solution improves, which is given by this green, the solution improves, but it is still far off from the exact solution. Okay? And as I said, if you want to get a better solution, then what you have to do? You have to reduce the step size, increase the number of steps, which becomes very expensive because you have to form the tangent stiffness matrix. Okay? So, what is the other alternative? Well, we will develop the incremental iterative technique, but before that let me show you that the unbalanced force. So, this red is the unbalanced force vector which keeps growing with the load step when you ignore the RU. When you do not ignore the RU, then also it grows, but the rate is reduced. Okay? Other alternative is one can use Rangakutta family of methods to reduce RU and get a better solution, but only change is how KT is calculated. But such methods are not used for practical problem, as we have much better technique such as incremental iterative technique. Okay? Why did I then discuss this? Because purely incremental solution techniques are simple and easy to understand. It tells you how a nonlinear problem is broken into a set of linearized problem, okay? But they are not used in practice. So, now let us talk about the incremental iterative solution scheme. So, let us say, so now we are talking about iterative scheme, right. So, let us say at the beginning of jth iteration of n plus 1th load step, that means the structure is at equilibrium in the nth load step. Now, I am imposing some more additional load to take it to the n plus 1th load step, and then I am iterating to satisfy my equilibrium equations. Okay. So, at jth iteration of the n plus 1th load steps, let us say my displacements are written like this, R superscript j, and the associated internal forces are written as R superscript I and j. Okay. So, when we begin the iteration in a load step, then we have R1, which is equal to the displacement at the nth load step, and the internal resisting force is equal to the internal resisting force at the nth load step, right. So, what is the unbalanced at the jth load step? The unbalanced force vector is equal to the external force vector minus the internal force vector. That is my unbalance, which is not equal to 0, and that is the reason we need to iterate to satisfy these equilibrium equations. Okay. So, at the end of jth iteration, we want to get solution R j plus 1. Okay. So, after jth iteration, basically we want to determine R j plus 1, where R j plus 1 is equal to R j plus delta R j, that satisfies the equilibrium equation. What is the equilibrium equation? The external force vector minus the internal force vector is equal to 0. These are my equilibrium equations. So, I want to satisfy that. So, therefore, I am writing that the external force vector minus the internal force vector at the j plus 1th iteration is equal to this. Okay. So, when I say at the beginning of jth iteration, at the end of jth iteration, that means it is basically I am talking about j plus 1th. At the end of j means I am talking about j plus 1th. Okay. So, now how do we derive such a method? So, you recall that RU is a nonlinear function of the displacement. So, RU j plus 1, that means the unbalanced force vector at the j plus 1th iteration is a function of Rj plus delta Rj. So, if I do a Taylor series expansion of this about Rj, then I can write it in this manner, where we have higher order terms that we are ignoring. Now, this, what is this? Well, if we use equation 1, which tells us the equation 1 is unbalanced force vector is equal to external force vector minus the internal resisting force vector. So, if I do partial derivative of this, okay, now Re is constant. So, this is 0 del Ri del R. Now, what is this quantity? This quantity is my tangent stiffness matrix KT. Okay. So, that means del Ru del R is equal to minus of del Ri del R, okay, which is the negative of the tangent stiffness matrix, right. Now, if I take this and substitute back here, then what I can do? I can write this in this manner, the tangent stiffness matrix at the jth iteration multiplied by the incremental displacement at the jth iteration is equal to this unbalance. So, this unbalance can be written as the external load minus the internal resisting force at the jth. So, the improved estimate for R n plus 1 is equal to whatever we had previously plus this new increment, right. Now, what we do? When I got this improved estimate of the displacement for R n plus 1, then I need to determine the internal resisting forces and check what is the new unbalance, which is this minus that. Okay. So, if this is satisfying a convergence criteria, which I will talk about in just a little bit, then we can stop the iteration. If not, we set j is equal to j plus 1 and solve equation 10 and repeat the same procedure again and again until a convergence criteria is satisfied. So, let me show you pictorially how does the Newton-Raphson iteration look like. So, here is R, the force vector, and here is the displacement vector. Let us say this is my exact solution path, right. We are here at the nth load step where we are in equilibrium. So, this is R n I, the internal resisting force, and this is R n, okay, the displacement vector at the nth load step. So, what we are doing? We have now applied this much of force. So, what is the unbalance? From here to here is the unbalance. That means, this is the unbalance. So, what I am doing? Unbalance for 1 degree of freedom problem, unbalance divided by the tangent stiffness is giving me this incremental displacement. But at this stage, this is the external force, but the internal force is here, because this is my exact curve, right. So, this is the internal force. So, this is the new unbalance, okay, for the j is equal to 2, right, and then we draw another tangent and come here. Okay. So, then this is the new unbalance. So, if I keep going like that, then eventually I come to the solution R n plus 1. Okay. So, here you have to form the tangent stiffness matrix at every iteration. So, therefore, it may be computationally expensive for larger systems. However, the convergence rate is very good, it is quadratic. That means, if the error after j is jth iteration is of order epsilon, then error after j plus 1 will be of the order of epsilon square. But for large system, KT formation can be expensive. So, can we modify it and make it little bit less expensive? Well, that is the idea of the modified Newton-Raphson iteration. There are two types of modified Newton-Raphson, one with constant stiffness and the other one is with initial stiffness. So, what is the constant stiffness iteration? So, let us say we are here at equilibrium, okay. Then I am actually drawing the tangent. So, it brings me here. Okay. So, this is the unbalanced force. Now, when I am not forming a tangent here, instead I am using the same tangent and going like that. Okay. So, this is the new unbalance, I am using the same tangent going like that. Okay. So, this is how we approach the final solution. You can see how many iterations are needed. Well, we need many more iteration as compared to the Newton-Raphson iteration, because the tangent stiffness matrix remain constant and it is equal to that formed at the beginning of the load step. Okay. So, convergence is slower as compared to Newton-Raphson. So, therefore, you require more number of iterations, but where are you saving? You are saving in forming the tangent stiffness matrix. You are forming it only once at the beginning of the load step. The other alternative is with initial stiffness iteration. Initial stiffness means you are not forming the tangent stiffness matrix even at the beginning of every load step, but you are forming it only at the beginning of the analysis. Okay. So, that means this is the tangent stiffness matrix, tangent stiffness that we will be using all throughout. Okay. So, this one will be used here. So, these are all parallel lines, right. So, here the convergence is going to be even slower than the constant stiffness iteration. Okay. So, you need to do more number of iteration, but you do not have to develop the tangent stiffness matrix, do not have to factorize it. Factorize means when you want to solve this problem, KT into delta R n is equal to your incremental external force plus R u n. Okay. Then when you solve this, you have to factorize KT. So, that is also computationally expensive. Okay. So, that can be avoided with this. So, effectiveness of Newton-Raphson or modified Newton-Raphson with Kt or K0 depends on the problem at hand. Okay. The Newton-Raphson is the most powerful amongst the three. However, modified Newton-Raphson can reduce the computational cost. Okay. So, like I said, in this course we are not going to talk about the implementation of the method. So, therefore, this I will skip. Okay. If you are interested, we can you can get in touch with me and we can talk about this. Okay. So, let me talk about the convergence criteria. When do we stop the iteration? So, we can use three different criteria: incremental displacement criteria, incremental unbalanced force criteria and energy criteria. What is this? At the jth iteration, I am looking at the L2 norm or the Euclidean norm of the displacement vector divided by the Euclidean norm of the displacement vector at the first iteration of a given load step. If it is less than a tolerance, then you can stop the iteration. Similarly, unbalanced force criteria is, this is the Euclidean norm of the unbalanced force vector at the jth iteration, normalized by that at the beginning of the nth load step or n plus 1th load step. That means the first iteration. It should be less than a tolerance. Okay. But there are problems with this, because what is the unit? So, when you have the displacement vector, you have translational degrees of freedom as well as rotation. So, they have different unit, right. When you take the L2 norm, okay, you cannot handle the unit, because it is getting basically what is L2 norm of a vector? It is square root of sum of squares. Okay. So, similarly, there are problems here. So, you may get good result for one force quantity, let us say axial force, may not get good result for moment. Instead, if you use the energy criteria, what is the energy criteria? This is my unbalanced force vector at the jth iteration, which is riding through the incremental displacement at the jth iteration. What is the work done? This is the work done. I am looking at this work with respect to the work done at the first iteration of that load step, and if it is less than this, some tolerance, then we are good to go. Okay. So, tolerance values must be selected with care. Okay. Smaller tolerance will give you better accuracy, but more computational cost. So, balance between accuracy and computational cost is desired. Typically, these values can be used where this is for displacement, this is for force, and this is for the energy criteria that I have talked about. And absolute form of this equation where this is not there, this is not there, this is not there can also be used. Okay. But I personally prefer this criteria the most. Okay. For nonlinear problems, I have used much smaller than this tolerance, but it should be okay, but that also depends on the problem at hand. Okay. So, these are the references that I have used. With that, I will stop in this lecture here. In the next lecture, what we will do? We will do one example to understand this Newton-Raphson and modified Newton-Raphson approach. We will do both hand calculation as well as OpenSys example. Thank you.